So we're going to keep picking on elements today. So over here, the red numbers on this table. So do you guys remember clear back last week what the red number represents with regard to subatomic particles in an element of that type? That's the number of protons. Yep, that's the number of protons. Very good. Well, fancy number, not to throw you off or anything, but they call the number of protons in a nucleus of an atom its atomic number. That's cool. Okay, that's it. What's a little more confusing, maybe not to you, but it's to me, is we use the symbol Z for the atomic number. We just do. Sure, I think it sounds German. Germans have a lot of things that begin with letters Z. So you guys told me last week that it's the electrons that are actually outside the nucleus, and if an atom, an individual cute little atom, is what we say neutral, then the number of protons that it has embedded in its nucleus are counteracted by electrons outside the cloud. So, and we'll talk today a little bit about atoms that aren't neutral, but if your atom is neutral, then the number of electrons is also equal to the number of protons. Okay, so Z is atomic number, A is mass number. Now you see what Z is atomic number, A is mass number. It's just the symbol. When you think of mass number, one of the things you need to get under your belt is it is an integer. It's a whole number. It's literally looking as you can into the nucleus of an atom and counting the protons, which you said was the atomic number, plus the number of neutrons that are also in the nucleus. There are nucleons. Okay, so it's a whole number. Yeah, mass number. And I don't know if you remember when we were talking about 3 subatomic particles, we said basically the electron is massless. So then that leaves the protons and neutrons that weigh about what we're going to say, I think it's on the 1 AMU. So the atomic number of protons is unique for an element. So, I mean, by golly, if somebody tells you protons, you know what that element is. Okay? So it gives you atomic number, you know protons, you know what the element is. So in other words, all atoms of the same element have the same atomic number. Okay? But and then atoms of different elements will have different atomic numbers. Okay. It's funny because you're like, you know, I don't know what alchemy used to do a long time ago, but if you figure it was silver and gold or something like that, I don't know. But if you want silver, you have to somehow, and if you're starting with chromium, notice that you have to somehow increase the number of protons in the nucleus of what? 34? 24, excuse me. 24 protons. But here in a minute, we're going to say it's not that easy to go ahead and to convince an element to be something else. The other thing is you have to bring along the neutrons too as you go, because there's like a sweet sort of situation between protons and neutrons. So, mass number, it's a counted number, it's an integer, and it's the number of protons plus the number of neutrons in the center of that particular atom. And it is not unique. It is not unique for an element. Okay? Atoms of the same element, we can say a couple different ways. Atoms of the same element can have different mass numbers. Sometimes, you know, what we're talking about here is the mass number, which is A, right? Mass number A is the number of protons plus the number of neutrons. My Z's, by the way, I don't do too many of them in chemistry, but the way I learned it to differentiate it from a 2 is to put like a little line through it. So that's just a habit. So anyway, if we can't have atoms of the same element with different mass numbers, the thing that we can change are the number of neutrons. That's exactly, if you're a picture person, that's kind of what we got going on here. atoms of different elements, this is kind of fun, atoms of different elements, so they have different atomic numbers, can have the same mass number by just kind of makeup neutrons. That's kind of neat. So what we're leading to is this idea of, now back to the same element with different mass numbers, this idea of isotopes. So isotopes are atoms of the same element, same number of protons in the nuclei, but they just have different number of neutrons. And we said that when it comes to weighing an atom, we're going to talk about atomic weight. When it comes to weighing an atom, the things that bring mass are protons and neutrons, so they will weigh differently. So isotopes differ by the number of neutrons in their nuclei. They have different mass numbers. All different ways to say it. Now, this is almost kind of like an oxymoronic sort of thing to say, but these actually are elements in nature that only have one, ratio of proton to neutron in their nuclei. They only have one isotopic form. That's kind of fun. Now, can you make a man-made form of these elements by forcing a neutron in? Yeah, but it's not a natural. These have two isotopic forms, and these have three or more isotopic forms. So this, I'm going to hand these around. These are the little fact sheets. Wouldn't it have been nice to use these on a test? But for this one, up here in the yellow area, you can kind of see the elements and their natural isotopic forms. The percentages next to them, and over here, it's this guy over here. The percentages is like on a counted basis, how many atoms in nature are that particular isotopic form. So I brought this book too. This is kind of an old one, 1987 to 88, but how much do these constants change? This is a book of physical and chemical properties of matter, elements, compounds. I kind of tease, it's like somebody had too much time in their hands to kind of gather all this. But it's some useful stuff if you ever need it. And there's a whole section in here, table of isotopes. And it says, I think it's neat if we take on oxygen. Oxygen has this many different entries for the different isotopic forms of oxygen, but notice only next to 3 of them do they naturally occur. And then I was kind of looking right before class, and one of these columns say how long, what their half-life is. Okay, so they're just not very stable. So anyway, that's just oxygen, and it's interesting. So, isotopes. Atoms of the same element, but they have different mass numbers because they have different number of neutrons in their nuclei. So there's going to be times when you need to say which isotopic form of an element you have. There's a few ways to do that. But bottom line, all you got to do is focus on give it the mass number, because then from the mass number you can go ahead and count the number of neutrons if you wanted to. We're going to do some examples like that. So the symbol for carbon is C, and carbon on this periodic table, it's got the number 6 there, so it has, every carbon atom has to have 6 protons, so that's its atomic number. So there are different isotopic forms of carbon. You probably heard of carbon 12, carbon 14 dating, carbon 13, carbon 14, 14. But carbon dating, different isotopic forms of carbon. This just has a carbon 12 and a carbon 13. So carbon 12, we could write the name, we could write the symbol, the dash, we could write the symbol for carbon, and then the upper, it's always in the upper left-hand corner would be the mass number. This is a little bit redundant, this one right here, because we have the mass number and the atomic number. So that last one is kind of preferred. It's nice, neat, concise. So this is where we put the symbol for the element. And like I said, in the upper left-hand corner will be the mass number. It's protons plus neutrons. And the lower left-hand corner, if it's there, will be the atomic number of protons. Here's boron, boron 10 and boron 11. Again, if we pick on boron, boron's got red number 5 up there, so it's got 5 protons in its nucleus. These both have 5 protons, but to make a mass number of 10, this one has 5 neutrons. To make a mass number of 11, this one has 6 neutrons. So on your test or whatever, you could be faced with something like this, where the symbol for fluorine, of course, is F. In this case, they're giving one isotopic form of fluorine. So in the upper left-hand corner, they're giving the mass number, which is protons plus neutrons. And then they went ahead and also gave us the atomic number, which is 9. Again, they wouldn't have to give us the 9 because you can pick it off of a periodic table. So the number of protons, of course, are 9. The number of electrons, since it's neutral, and I'll kind of show you something that's not neutral, but just generally speaking, if in the upper right-hand corner it does not have a it doesn't have a symbol and a number, symbol and or number, then you know it's neutral. So right up here, this right here, okay? So it must have 9 electrons too. And we can get the number of neutrons by difference. So it's the big number minus the little number. Number of neutrons would be the mass number minus the atomic number. So remember, those are all going to be whole numbers. Always going to be whole numbers. Always, always. They're counted. We'll be talking more about ions later, but I kind of want to give you an introduction or just to kind of remind you how that works. A minute ago, we picked on fluorine. We said it was neutral. So it says 9 protons and 9 electrons. Well, there are some atoms that tend to want to lose electrons and some atoms that tend to want to gain electrons. I'll kind of tell on myself, years ago, I'd be like, now I know that there's positively charged and negatively charged species we call ions. But now, do they lose and gain electrons or do they lose and gain protons? I know it's a small thing, but if you picture an atom, they're not going to lose and gain protons. They're going to lose and gain electrons because they're the outermost subatomic particle. So we have these 2 options with regard to electrons coming and going. For cation, sometimes pronounced cation, no. You think of the cat, the big T there, okay? Cations are positively charged. Like, well, how could something become positively charged with regard to electrons? Well, it must have lost an electron or 2 to become positively charged. That's exactly what they do. Bless you. Then the other option we have is where something picks up electrons. So anions, not to be confused with anions, are negatively charged. And again, how can they become negatively charged with regard to electrons? They must be gaining electrons. Okay, 1 or 2 or 3 or 4. So now with an ion, we go ahead and we still have the mass, the big number on the upper left-hand corner and the small number on the lower left-hand corner. But now we have a symbol, either plus or minus, and then a number in the upper right-hand corner, which indicates its charge. So a cation would look like this, and an anion would look like this. Okay. So again, we're going to talk more about why an atom would lose electrons or gain electrons, but that's just kind of a notation. Now we should be able to, given the isotopic information for an ion, we should be able to go ahead and say how many subatomic particles it has. So for instance, calcium. As some of you might remember, calcium along with its buddies, beryllium, strontium, barium, radium, and magnesium, it tends to kick off 2 electrons. I say kick off 2 electrons because you can see that +2 in the upper right-hand corner. I'll go ahead and when we get to doing more about ions, I'm bad about 2+ or +2, they're the same thing. But we could go ahead and answer these same three questions. So how many protons does it have? 20. How many electrons does it have? 18. How many neutrons does it have? 19. Okay. So the 20 was from this number, The 18 came from 20 minus 2. So that was the number of protons, and that was the charge. And then, of course, the 19 came from 39 minus 20. That's the number of protons and neutrons, and that's the number of protons. So, yeah, you're going to want to be able to do that sort of thing. Well, let's do an anion. Chlorine, and I just think the periodic table is so cool. These things are called families. They all do similar things. So chlorine, bromine, fluorine, iodine, and acetine, they all tend to pick up 1 electron, okay? And so here we go. So how many protons does it have? 17, perfect. And then how many electrons? 18, and how'd you get 18? Yep, 17 plus 1, yep. How many neutrons? I'd get a calculator out because I usually mess these up. What? I'm like a 19 also. And you got that from 36 minus 17. Very good. Yep. Okay. I've got some slides now that kind of wrap things up, and I could have been maybe kind of going back and forth, just to give you a little bit of more insight in how an atom kind of does its thing. This force is actually talking about the attractive force between the protons and the electrons. And the d there is the distance between those subatomic particles. And this symbol right here is actually what we call the proportionality symbol. And it simply says as the force will increase as the charges increase, and it will then decrease as the square of the distance. So I've got some examples here. We said chlorine will form a -1 charge, and as it turns out, as you maybe remember, like sodium, lithium, potassium, rubidium, cesium, francium, they'll form a +1. So we have a -1 and a +1 ion. Those red lines right there are kind of showing you the length of the red line, the arrow, shows you magnitude. I do this all the time. So how would you compare the magnitude of the forces there? Like between this pair of cation and this pair of cation. Which one's stronger? The 2, exactly. All that's saying is kind of intuitively, you might imagine, they're drawn closer together, or they're drawn by a stronger force. And then we have this sort of deal where we literally, now that black thing, these black things are the nuclei, and that kind of ghosty looking thing would be the electron cloud. So we kind of talked that most matter is empty space. It's just kind of fun. But anyway, that's not my point. Kind of the electron cloud, what it's doing kind of separates the two. So here we have 2 nuclei that are relatively close together, and they would have relatively strong attractive force. And here we have 2 nuclei that are farther from each other. The most likely reason that they are farther from each other is that electron cloud is not letting them be as close together. Sodium and chlorine, magnesium and oxygen. So this is an example of that first, where we have a +1 and a -1 and a +2 and a -2. This was, I said, remember I said a minute ago, if you're going to try to turn chromium into silver, well, okay, you got to mess with your protons, but you also got to mess with your neutrons. What this is showing you is that there's kind of a band of stability, or then outside the band of stability would be instability. With regard to the likelihood, proton, that's the type of element. We could go along here and we could say, that's, uranium's up here at 92. Atomic number 26, I know, is iron. These are elements. And up here is the number of neutrons generally in a nucleus of that type of element with that type of element, that are protons. And you can kind of see that it's not always a one-to-one relationship with regard to it being stable or unstable. I think this is good. All right. So, Harvey will do on. Thank you. Yes. So let's go on to the next part. All right. So how much does an atom weigh? How much does a woodchuck? Yeah. How much does an atom weigh? We already said that what subatomic particles of the three bring mass or weight to an atom? The neutrons and the protons. Yep, the neutrons and the protons. So as we talk about the weight of an atom, know that that's kind of where it's coming from in general. So I'll just go ahead and tell you. So we've talked about the whole number. That's the atomic number of protons. Most periodic tables have three things for each box. They have the symbol of the element, they have the atomic number, and then they'll have what I call the decimal number. The decimal number is the average atomic weight. Decimal number. Notice units that we use for average atomic weight are not pounds or kilograms. They're another unit called atomic mass units. So average atomic weight. Right off the bat, since we talked about isotopes this afternoon, you know that like a carbon-12 atom will weigh less than a carbon-13. Okay, so somehow when we pick on carbon, we have to take that into consideration. So that's why it says that those decimal numbers are obtained from a representative sample of that element in nature. Synonyms for average atomic weight are average atomic mass, atomic weight, or atomic mass. They all mean the same thing. So like I said, we're going to have to take into consideration what Mother Nature gives us before we come up with a single decimal number up on a periodic table. I'll warn you that every once in a while the average atomic weights change on periodic tables. Like, oh, are you serious? And all I can think of is that they've updated their isotopic information. So we're going to actually walk through a problem where you calculate the decimal number. You calculate the decimal number based upon how abundant each isotope is in nature and how much an atom of that particular isotope weighs. So we always need standards. It needs to go back to something. And as it turns out, the standard for an atomic mass unit, sometimes called a U, like I learned it as AMUs, atomic mass units. And then I'd use a textbook that used U's, and now this textbook uses AMUs again. So by definition, if you pick on that one isotopic form of carbon-12, carbon-12 with 6 protons and 6 neutrons, then it will weigh exactly 12 atomic mass units. And then other masses are relative to that. So an atomic mass unit in terms of a gram is this. You think you have to memorize that? No. You think that's approximate? There is uncertainty. That's to 4 sig figs. But instead of memorizing it that way, it makes sense. One AMU is very light, so it's 1.661 times 10 to the minus 24 grams. That number I can't remember, but this number I can. We can say, and some of you guys might recognize that's Avogadro's number. 1 gram, and again, it's approximate, is approximately equal to 6.022 times 10 to the 23rd AMUs. So if I am going to memorize something, that's what I'm going to memorize. And that's not an accident. It all kind of comes down to the definition of a mole. Okay, so how do you come up with those decimal numbers? Well, someone needs to give you information about the particular element of interest. They need to say what the isotopes are, what the possible isotopes are, what an atom of that type of isotope weighs, and how what we say abundant it is. When I passed this around a little bit ago, you can kind of see the blah, blah, and there were percents listed. And that means in nature, this is a counting number, out of so many atoms of of that type of element, okay, how many of them are that particular isotope? That's how that goes. We pick on hydrogen. Hydrogen has 2 isotopic forms. It's pretty crazy. Its most abundant isotopic form is 99.99%. That's hydrogen 1. Hydrogen 2, affectionately called deuterium, then is 99.98% for hydrogen 1, and then deuterium's 0.02%. So, but it's not always that lopsided. That hydrogen is really lopsided. So, for instance, we're going to kind of walk through this process with copper. There are 2 isotopic forms of copper. Copper 63 and copper 65. Yeah, this abundant information is different than that abundant information. Like, Gavin, can't you agree on anything? So, I just gotta double check. Yeah, these 2 agree. Well, they're from the same manufacturer, probably. Anyway, we're going to go with this information about isotopes. So which one is heavier, copper 63 or copper 65? 65 is heavier. Yep, it will be heavier. Which one's more abundant, copper 63 or 65? 63 is more abundant. It's about 70% 63 and about 30% is the other, the heavier one. Yep. So what this means is if you were to have not 100, if you were to have 100, you had about 69 of them would be copper 63, about 31 of them would be copper 65. But if you were to go ahead and have, not 100, but 10,000 copper atoms, and you were to divvy them up into piles with 2 isotopes, 6,909 of them would be the lighter isotope, and then 3,091 of them would be the heavier isotope. So that's what that means. This is a table with some other elements. So I mentioned hydrogen and deuterium. Notice this actually shows a 3rd isotopic form of hydrogen. It's called tritium, but this asterisk means that it's not very stable. So with isotopic information, or to do a problem I'm going to show you how to do, you need to know its percent abundance, we just talked about, but you also need to know how much an atom of that type of element weighs. Okay, so those are 2 pieces of information you've got to have. Neon down here, let's see, is that a good example? Magnesium isn't bad. So here are 3 isotopic forms of magnesium. That's their relative abundances. This is how much each one weighs. This would be their mass numbers. This right here, by the way, is what the periodic table says. So somehow we need to get from this information to this information. This is showing you fluorine, chlorine, magnesium, and lead. And the different colors mean different isotopic forms, just to kind of give you a visual of what that would look like. Yeah, we saw summation before. Anytime you see this, this is the Greek letter capital sigma. And what that means is summation. Yeah, you guys used it when you calculated your relative standard deviations. So what you're going to do for each isotope is those last 2 columns you saw a minute ago. One was the last one was the percent, and the one before it was the how much it weighed. You're going to use those 2 columns for each isotope. You're going to take how much it weighs, that's this one, times its fractional abundance. And fractional abundance, I don't know if I have it on here, but fractional abundance is the percent abundance divided by 100. That'll get you back to fractional. So applying the summation can be thought of kind of like this. Let's just say we have, for that first isotopic form, we're going to take its weight times its fractional abundance. We're going to add to that for the second isotope, how much it weighs and its fractional abundance. Third isotope, okay, etc. Then we draw a line and we add these up. Oops, this is my big plus sign. Add them up. And then whatever this number is, that is your weighted average. That is your average atomic weight. All right. Let's do this thing. Yeah, I guess I did input it. So fractional abundance, you're usually given percent abundance, which is parts per 100. You get parts per 1, you divide by 100. Well, here we go. We're going to go ahead and knock this out. Now, in order to apply what I just said, not only now do we need to know how abundant they are, but this last column has been added. We need to know how much each one weighs. Notice units are AMUs. All right. So we'll only have 2 terms, which is kind of nice. Our first term will look like this. For the copper 63, we take how much it weighs, which is 62.930, times its fractional abundance, which is percent abundance, divided by 100. And we're going to add to that what is contributed by the other isotope, 65. So for copper 65, we have these 2 terms. How much a copper 65 atom weighs. Then the second term is its percent abundance over 100. So this was for the Cu63, Cu65. Cool. Seems kind of anticlimactic. I've been all over you guys about how you round your answers, okay? And for a problem like this, I'm going to just kind of give you a general rule which will be consistent with what we talked about before, and also isotopic information you're most likely given. If it is a relatively light average atomic weight, you're calculating from isotopic information, light being less than 10. Okay, so then that only leaves you with kind of, because boron's 10.811. So basically beryllium, lithium, helium, and hydrogen, go ahead and give me 3 decimals. Otherwise, give me 2 decimals. And actually, that's kind of what you justified if you look at the uncertainty. It's probably 3. So I got 2 decimals. This is one of the very few, and you will have one of these on your Unit 1 exam, I promise you. There will be a problem like this on your Unit 1 exam. But can you see where this is one of the few things, and how can you check your answer?
You got it on your email.
You get what?
You got it on your Canvas thing.
No, on your test. What if you're on your test? How can you check your answer?
It's in between the 2 numbers that they use.
If between the 2 numbers, there's even something more specific than that. But yes, that's true. That's between the 2 numbers. What do you think? Remember in your test, you get a black and white periodic table, kind of like the one in your book, or one in your notes.
Oh, isn't that the atomic weight?
Yep, that should match up with the one you got in your notes. Like, okay, all those decimal numbers, and like I said, you know, sometimes they change, they get tweaked because we have different abundance information. But all those numbers came, all decimal numbers came from applying the same process. Cool. So yeah, I like what you said about it needs to be in between, for sure. But notice that y is 63.55, y is not dead center. For the simple average is you add 2 and divide by 2. Y is kind of off center. Because they aren't both 50%, yeah. It's going to be kind of skewed over here to this side because we've got more of it. Yep, that's why it's called a weighted average. So kind of visually, this is what we have going on. You would expect it to be maybe right about 64, but exactly what you said, we have more of this isotope, so it's skewed over here. I told you hydrogen's crazy. This is called deuterium, this guy with mass number of 2. Let's look at this one right here. So this is normal hydrogen, and what, 99.98% of hydrogen is mass number 1. Talk me through how many subatomic particles this has. Okay, I'm gonna go ahead and put a 1 down here. Does that seem okay to y'all? Because this is the mass number, and then this is the atomic number, and hydrogen's atomic number 1. So how many protons does it have? 1. How many electrons does it have?
1.
1. Yep. How many neutrons does it have?
0.
That's my point, exactly. I just think that is so funny. It has 0 neutrons. Does that make sense? It's just like a naked proton. But that's not my point. So my point here is, like, it's so heavy this way. That's why, so what is the average atomic weight of hydrogen? What's the decimal number? 1.008. Thank you. That's actually that's a number that we use hydrogen so much in our calculations. That one, you don't have to memorize it because you'll have a periodic table for your test, but that just, oh my gosh, 1.008. It's like carbon's 12.01. Yeah. So that's why it's clear over here than having much of this characteristic at all. Yep. Very good. Well, dang it, people, we got to the end of this one too. So these will also be due on Wednesday. Okay? But remember, you can check your answer. Okay. I think that's enough for today.
Jacob, do you sure it's okay for this week? It's just good for this week?
Yeah.
Yes, yeah.
So you asked about if you want, I'm going to go back to my office and grade those right quick. It won't take me very long. If you give me, I'll be here till 3, so anywhere between 1:30 and 3, if you want to stop by and pick up your graded labs, you can. Does that make sense? Okay.
After do it, actually.
Okay.
I work at the hotel so much, I love it.
Yeah, we live in that.
I don't know why. I have to go to the store again this week. I'll be there Wednesday.
You have to be at the store too.
What?
You have to be at the store too.
I hate this. I worked at the store this weekend, and whoever was Leslie, whatever her name is, she left early. So, and I care, because she gave me yesterday.
I was working alone for a few months. They all came to wage.